I'm going to do it. Hey, it's Coffee Compiler Club. We're here to talk today about where the word yellowtail comes from or reminds people of, and Australian wines or not, or beers or not, or coffee and compilers or not. I don't know. We had a funny, go around while waiting for folks to join up. You're all being videoed. You'll be up on YouTube, presumably within a couple hours. Depends on how much wine gets drunk this afternoon. I have my own guest coming over, and we're going to go check out things there. Yellow Dog Linux. There it is. Okay, fine. No set agenda. All of you have heard this before, so I think we're good to go here. Matt showed up. Let me do that. All right. Anyone want to start with something? No, I'll throw out the stupid AA, nothing going on. I went around and around and discovered I was having what I considered unacceptable precision losses around values that escape the local compilation unit and then get passed back in because you handed out a callback and the callback calls you back. So I went around and tried to go update that and discovered a screw up in my current set of lattices. So I'm off busy rewriting the fourth time around the core lattice gut, not the core lattice guts, the lattice guts in and around things that look like scalars that get passed about. So it's been a week of cleaning up tech debt, basically. No surprise. Other than that, no.
One thing I realized recently, I think a few days ago, was I was implementing functions like average and sum and product for the standard library, and a colleague of mine said, well, you should have a look at the Wikipedia page so you get a full set of statistical or whatever functions. And I had a look at it and I saw, hey, there is like a correlation between, of course, there's a correlation between sum and average, but then I learned, okay, for product, there is like its own mean function that's kind of like what average is to sum, geometric mean is to product. And I thought, well, that's cool, let's implement this. Then I had a look at the formula. The formula needed exponentiation. I said, well, how hard can that be? I had a look at the x86 instruction set. Said, well, there is no instruction for it. There is not even a instruction for parts of it.
Yeah.
And then
it's
really, really ugly. So if I think the easiest way to find ugly code is to write down math.pow in a Java IDE and just navigate to it. And oh man, that's not only incredibly ugly code, but it's also really, really long. And that's when I decided, well, maybe I will not implement that geometric mean function that day.
C2 actually has the inline x86 instructions for doing the correct version of exponentiation and POW. And it's custom IR just for x86, and it spews out a pile of custom IR, and then in the core guts, that parts of exponentiation and the other parts and the left parts end up in a loop somewhere. And I did it 20 years ago as a Jesus Christ, I have to do this thing, and then never looked at it again. Ah!
So incredibly ugly with like special constants and refinements. That's if you like, you can share your screen and navigate.
Oh, you lost your sound.
You can, if you want, you can share your screen with like navigating to math.pow, and then
I put it up on public share.
Oh yeah, that works too.
Okay, I have to figure out math. Yeah, you're talking about the Java math.pow.
And I mean, of course, there are probably intrinsics involved and everything, but the straight Java code is scary enough.
Well, to be honest, if the x86 assembly would have a function for that, the Java code would be way scarier, but unfortunately it doesn't.
It's like, you know, the x86 guys, like, there's only so much hardware you can do for this shit
Sure.
if you want to handle all the infinite corner cases of IEEE spec. You're like infinite underflow and partial underflow and overflow and partial overflow and on and on and on and on and on. Precision losses, so you have to shift scale first before you can start doing other things, whatever the hell. It's just like, nah. So there's a lot of normalization loops going on, followed by one or two magic ops, followed by renormalization loops for the other way and stuff like that. It's just,
Yep.
and yeah, and the normalization loops are checking certain range, out of range bits. So that's the funny magic constants. That if you turn into a pile of bits and you just compare them as a pile of bits against another pile of bits, even though they're both ostensibly floating point numbers, but you treat them like raw integer bits, you could test bits. Turns into something. Okay, I made it shareable if you wanted to grab the screen and share. I don't have the source to math.pow popping up in my IDE, but didn't ask it right. Oh, let me do it this way. Java Lang. Let's see if it'll do it. Math. Okay, here we go. POW calls strict math POW. That didn't help any. Which calls fdlim POW compute.
And
Oh, Jesus. Okay, fine.
I
Yeah,
think another indirection and then you're there.
I'm sorry.
Another indirection and then you're there, I
And then you're
think.
there. Yes, yes. All right, here we go. We'll do this thing. Of course, my IDE is like ludicrous for this go. Here go. See what happens here. I'm not on readable mode. I think I started from math, POW, and then you know, I go strict math POW. It's not necessary to be able to read this, which goes to fdlibim POW compute, which goes to this, which, you know, you can see scrolls on and 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 on. This is all one function, and on and on. So, you know, holy crap. And just
Oh, at least it got comments.
Under overflow if x is not close to 1. Yeah, there's every now and then. C is 1 over, yeah, okay, absolute value, you know. Of course, it's pretty obvious what those are doing, but now why? There's this comment, by the way, which is unreadable in any case and has lists of 19 special cases. Yes, I read that right. Yes, 19 special cases. Probably it's been badly formatted by the IntelliJ, and it actually ought to be a table and not just special cases 1, 2, 3, 4, 5, 10, all crammed together.
Click on the edit. Ah, never
Oh,
mind.
well, okay.
So what I was wondering, does anyone else have stories like this where you thought, okay, this is totally simple, or there has to be instruction for it, and then like a few hours later you realized, okay, this is probably its own PhD thesis or something?
Not necessarily like that, but unfortunately I can't find the source code location anymore, but something along the executor framework in Java, there was actually a comment in Duck We Trust. Like, nobody understands that code, but Doug Lee wrote it, so nobody's touching it.
I've worked a lot with Doug Lee's fork join and the tasks and the continuations and stuff code. That was H2O was built on that, an early version of that. And I got to where I finally understood it after using it, you know, in anger for 2 or 3 years and trying to run a company off of it. So I claim there is a method to his madness. And you know, I took some inspiration about what I do from some of the madness that came out of that. But he and I are two I won't say two peas in a pod, but we're both pretty far out on the spectrum in different directions.
He also does not like white space.
Yeah.
Yeah. And having read the code, I kind of got it. In a lot of places, it's like, yeah, okay, I get it.
And I thought you wanted to end your sentence with evil mastermind or something.
I'm not up to calling Doug an evil.
But you call yourself that. Okay, good to know.
Where's the Doom code for doing, I want to say, not fast square roots or something.
That was good.
Yeah, yes. I think
That was
that went
brilliant.
around as a meme.
Yeah, it's fast inverse square root is the Wikipedia page. I have a bookmark.
Fast inverse square root. That sounds good.
It's kind of fun to read the edits,
Comments.
you know, the like various like random people just want to delete the word like what the fuck in one of the comments, and then
Oh,
like,
yeah, right.
Edit more.
Oh, and the Wikipedia page now has a long, well-written description of what the hell's going on. Somebody has done a proper job of explaining and showing off the accuracy of the results and all kinds of stuff there.
That was probably himself.
It could have been. Came along later and did a bunch of stuff.
There's absolutely no way he wrote a Wikipedia article. It could be like Superman eating kryptonite for breakfast.
If you read the Wikipedia page, it's actually not John Carmack who wrote the code. He like borrowed it from like these other people.
Oh, it's often misattributed to John Carmack, but it was actually based on an unpublished paper by Khan. Oh, geez.
God.
And there's SSC instructions, new ones that I have not seen before for doing it, so you don't have to do it anymore. Yeah, and Cordic libs. I think I have used Cordic libs before. Somewhere in the early versions of Hotspot, when we needed floating point to work everywhere and be bit precision accurate, we just grabbed softlib. And it was quite a few years later that we made the JIT spit out the x86 ops if you had the correct kind of hardware, and it was the correct era because they were faster or slower according to the era, and added all the extra ops around it. There you go, to get you the bit precision that the Java spec demanded. And at the same time, we were getting slammed by the C community that like sign sucked because we were super slow because there was a sign op, but the sign op from x86 didn't do the low bit precision accuracy demanded by the spec.
Look at the authors on this though. It could be an ACM paper.
Oh, you have to get closer to the camera. Too low resolution, but it's fine. Yeah, I believe you. Whoa, there you go. I picked the wrong button. I messed my chair up. Can't walk, talk, and fix my chair at the same time. Fine. All right, are we done whining about x86? No, about IEEE spec implementations in x86 and Java for POW. Yeah, grab softlib and walk away, and then come around and visit later. If you become to a point where it's super hot and super exciting, and everyone really badly wants it, then there's a way to go. There's a path forward. But
oh, I had a topic for discussion. So it was just so we discussed this a bit on Discord, and then I was like, this is getting a really long topic, so we should discuss it here. So it's our reference semantics versus value semantics.
Arcing cows.
Whether copying should be implicit or explicit, and whether, immutability, should be this deep property of a value so that, you have a value that's immutable and you can't modify it, or whether it should be like, oh, well, actually, it's immutable, but it's an immutable reference. So like if you change the reference, the actual
const pointer versus const structure. Yeah.
So I don't know.
And Pony goes deep and
I'm not sure what there is to say about it, honestly. I mean, I know, Swift, I guess Swift is the place to start because they have this value semantics in their language for like collections and stuff.
And they only copy occasionally. And they don't tell you when they messed up and had to copy. That goes straight to my easy versus fast. If I want fast, I explicitly want no copies that I don't specifically excuse on the spot. And that's part of the whole C community performance complaint about a lot of these languages. You get hidden copies, that's your cost. It's hidden, you can't see it, and also that turns into the 90% cost. So I want a way to make it visible and shut it down. And then that makes me change how I code. And then that's the price I'm willing to pay if that's hot code.
Well, I mean, there's also like, I mean, the one I like, I mean, I'll come out and say what my, bias is I like implicit copies, but with like a guaranteed copy optimization. So like if you write your code in a certain way where it doesn't reuse old values, then you're guaranteed that it will destructively update. And there's
100% with that, as long as that guarantee, when it's going to fail, you get it's not a guarantee if it can fail silently. So if it fails with a warning that says, hey, and I'm going to copy here, or an error, hey, I can't make this note non-copying, I have to do something, you have to excuse it. You have to change your program text to say, and here it's okay. That's the kind of goal I'm headed for. And then Matt asks in chat, and he has mic issues, so I'm just going to say it out. Don't hide the copy. Language designer's goal to make this as rare as possible. So you have to annotate like tiny percent of the code that is explicit copies, then that's not likely a big deal. And vastly preferable to the hidden performance cliffs, yes, cliffs, with implicit copying. Alan, you're.
Oh, well, I was trying to read the chat.
Gotcha. Yes.
I mean,
you have the God glow behind your head coming and going. It's like God is turning the lights on and off behind you.
Let me try turning on the light. Let's see if this helps.
It's very fun to watch. No, it's the window on your left, and whether or not the camera decides to, backlight or not, or whatever, it does some sort of.
I mean, it's a little better with the light, I think.
Okay. It is more consistent right now. You're still coming and going, though.
Yeah.
It's all good. I don't know. Now we're on the same page, right? So the issue with cow is if it has to copy, then it's a silent copy, and
yeah. Well, I mean, as I said, it's a guaranteed optimization, so you can put in a warning that your code isn't the right kind of code that can be optimized.
Yeah,
so
I think that's good. So that just says you have value
It's a little tricky, but
it's
possible. So.
Say again, I'm sorry.
I said it's a little tricky to put a warning in that your code isn't optimizable, but I think you can do it. I think it's not. I mean, like you can warn that you're copying a big array, for example. Like you could say this array should not be copied, and then you'll warn when it does copy.
Right. There's a not silent response, and now if I do some sort of a casty thing or a type annotation thing, then the warning goes away. And I can tell the compiler warnings are errors, and now I can say that if I have a big array copy, that's an error, and I'll get told it's an error, and I can go fix it. I think that's a perfectly reasonable.
Right, and so then but then you got these people who say, "Oh, well, if you're going to have a warning like that, you should have a type system that enforces it."
Well, that's what I'm saying. If you have a warning, that's already the type system enforcing it. You just have the option to change between a warning to an error.
Mm-hmm.
And that you've already got you have told your type system, and here I couldn't, and now it's part of the language spec. And here the language spec says he gives you an error message or warning message saying, I'm going to copy. Fine. Yeah. That's my one special take on that. Like the whole ARC and cow things all have the problem that when they don't work, you silently get the copy. And then that's the issue. It's silent. And then now like everyone, I think everyone agrees, we want the annotations to be rarely required annotations.
Mm-hmm.
Are we done? We beat this out on Discord for future viewers. We beat this out on Discord. I'm going to say I can't read the Discord to look backwards and see. The only thing was Alan's blacklist of people whose language choices not to trust, which includes Alan and me both.
I would. Can ping me later. I would be interested in this list.
Yeah, well, I couldn't find a good thing for Simon because I like all his choices.
Too many keywords. But that's why you don't trust me. That's why you shouldn't trust me.
All the keywords are the same length. Can never trust anyone who does that.
Oh, I see. Yeah, mine are all the same length too. They're all 0.
Yeah, he's got you beat, Simon.
What was the bull about? Injection library called bull. Okay, cows, bulls, cow arcs. I'm trying to see. There's one. What else? There's a giant long Discord chat. That was fun. All right. Reducing accidental C++ accidental complexity. Oh, geez. Okay, fine. I'm done. We have another topic here. We're going through them fast.
I have a topic update, I guess. Like basically the last couple of weeks, I've been rewriting my Typecheker because there are a bunch of bugs, and in the past I was like, let's slap a hack on it and continue working on what I was doing before.
That was my status update for AA too.
But so I reached a point where in my my language supports self types, as they're usually called, which basically you write self as a type. And if you do that in an interface, it will be the type of whatever implements that interface. And inside a class, for example, it's basically just syntax sugar for referring to the class itself. So the prime example is you have a clone interface, which defines a clone function which returns self. And then if you implement that for, say, string, and you do string clone, the compiler says, oh, it returns a string and not a clone interface, for example. And so Inko has that because I thought, oh, that's pretty neat. And admittedly, I only use it in very few places.
Don't do what Java did. It's fine.
I don't know what Java did, but so I the problem here is basically self. At least in the way I implemented it, self is a type, but it's also not, in the sense that you can't, like if you take it in its raw form, so you have your compiler data structure to represent the type, and you have some sort of flag, whatever, that says this is a self type, you can't do anything with it. Like you don't know what functions it has, whatever. So basically, every single time you do something on types, you have to basically resolve that self type into its actual thing. And so every single time you call a method, you type check, you read a field, whatever, you have to handle the case like, oh, what if it's a self type? And unsurprisingly, you end up with bugs. Because I have this code where you basically end up with a lot of functions where you say, oh, hey, if you encounter a self type, replace it with this thing.
Do you enforce the self resolution right away as soon as you encounter it?
No, so if you stick it in a function in an interface or trait in this case, the actual type stays as self.
Mm-hmm.
If you stick it, I think if you stick it in a class, it still remains so, but in theory, you could resolve it right away.
Mm-hmm.
But I do try to do it early. So if you call a method, for example, and it returns self, it resolves it as part of that call, not some point later on.
Okay.
But you still end up having to tell it, what do I have to resolve it to? And unsurprisingly, you will occasionally pass it the wrong thing. So I ran into this compiler bug where in my native code, if closures capture certain values, I don't remember the full extent, I think if they captured a field or something that was typed as self, it would end up resolving that to the closure, not the thing that it was captured from. And then somewhere deep down, you would get this error when it tried to discard the value because it was doing it completely wrong. So just figuring that out took me like 5 days, which kind of shows how annoying it is to support self-types. And that was like, I don't know, the 15th time I encountered a problem like this. So I was like, okay, that's it. We're getting rid of it. Because I looked at where I used it, and so I have it in two places. You can use it as a type or in a static function defined on a class. You can use it as a constructor of that type. So my syntax for creating instance here, you have the type name, curly braces, fields in between. You can replace the type name with self. And this was basically me being extremely lazy. So you can write self curly braces instead of like list curly braces.
But self is a type on its own. You can pass it
So
around like
within, well, so it's more like I guess it's kind of like a late binding kind of type.
Yeah.
And basically syntax sugar. And I think out of all cases where the word self occurred, 9 out of 10 times it was me being lazy, not wanting to write the full type name. And the only legitimate case where I used it was in the clone interface as the return type. Well, and then a couple of interfaces used for implementing operators, where they said, hey, this interface defines the minus operator and expects an argument of type self, a reference to it specifically. But those I had already scheduled to refactor because there were actually a few cases where, for example, I had a type representing a monotonic clock that implements the add operator, but adding 2 monotonic clock values together makes no sense. It's like saying, oh, add 5 minutes ago plus 2 minutes in the future. Like, what? So I wanted to implement it so that you could say, hey, we add a instant, as this type is called, with a duration representing a span of time, because that does make sense. So I changed the add interface to be generic. And that's something I wanted to do with the other operator traits as well. Because although technically rare that you want to have A divided by B with them being different types, but it's more for the sake of consistency. So basically, out of all the cases, the only one where I felt it was justified was in the clone trait as the return type. And there's like, yeah, okay, but you might as well just make that trait generic. Like it's clone generic over R, and clone the function returns whatever the hell R is. And yes, then in a type signature you have to write clone, brackets, whatever string, but you basically never do that anyway. But so that sent me down a rabbit hole. It's like, okay, let's remove self types. Oh boy. Because through that, I discovered that my compiler does not handle recursive types very well.
Yeah.
The example I ran into is I had an equal trait, which was defined as requiring a function called double equals in this case, which takes an argument of a reference to self and it returns a Boolean, as you basically would expect. Well, with self types out of the window, that would have to become a generic trait. And the argument would be a reference to, that generic argument, T, for example. Then in my unit testing library, I had a function that would expect or would test if 2 values were equal. And so that function was defined as being a generic function, which expects some type parameter T, which implements equal over T itself. So that if you give it an int, it knows, oh wait, we expect int to be equal to int. Yeah, my compiler didn't like that, because it would keep type checking. Basically what happens, you pass it int, and it would then check, I have to say correctly, because this also took me like 2 weeks to figure out. But basically it ends up checking like int against equal, then against parameter, then int. Either way, it gets stuck in a loop, basically. And then through that, I found a bunch of other bugs where based on the type on the left and the right of your comparison, so your source and whatever you're comparing to, as part of the type checking process, I have some data structures so that when it encounters certain type parameters, it knows like, oh wait, in this context, that type parameter is assigned to this thing. An example is if you call a function with multiple arguments, what I did is I created such a structure to store all the type parameters for the type arguments for the receiving type of the method call, and of those parameters that the method itself defines. The idea being that if I have 3 arguments that refer to the same type parameter, the first time I check against it, I assign it, and then the second and third argument, I just reuse it. Well, under very specific cases, my compiler would overwrite that assignment. And so it would either end up comparing against the wrong types or treat something as valid when it was not. So that's been what I spent the last 3 weeks on trying to fix that, of which I think I spent 1.5 weeks trying to procrastinate and basically try to be like, no, I don't want to do this, because every time I've had to do these kind of changes, you end up with like 5,000 compiler errors. And the thing what Rust does as a compiler is it has a limit on how many errors it will display. I don't think it's like a fixed number. It's more based on things like the order of things. Either way, it's specific. But in practice, with these very large scale refactorings, what happens is you will get like 200 compiler errors. You'll spend 3 weeks fixing them. And it's like, oh, by the way, there was actually 100 more that we didn't tell you about before. And the thing is, it also won't show certain errors if others occur. Like it's based on how it checks aborts early. So once you fix your 500 compiler errors, then you find out the code you originally wrote 2 weeks ago doesn't actually work because there's some other issues with it.
Right.
So I spent a long time trying to figure out how the hell am I going to refactor a Typecheker that's, you know, mostly due to formatting, it's like, I don't know, 5,000 lines long in total, that is used everywhere in the compiler.
Did you try to minimize your type system to some kind of minimal core that you sure the type system, you know what the type system is doing?
No. Well, in a sense that I try to minimize it. Like I don't have plans for like higher kinded types and all the more sort of expert Haskell-y level kind of type features. I try to keep it to a point where the average person can understand it.
Yeah,
but simply the presence of traits and generics makes things really complicated.
Yep.
And then I do have this one thing that I took from Rust where if you implement a trait for a class, you can say, oh, by the way, this trait is only available if these additional conditions are met. So you can do something like, oh, implement the equal trait for array, but only if the values in that array also implement equal to itself, for example. I very vaguely called them trait bounds because they're bounded by additional clauses. It's a terrible name, but that's the best I could come up with. But that complicates the process as part of your type checking. And specifically, the difficulty there is that normally the comparison is like you have your type on the left. It has a sort of source of type arguments to look type parameters up from. You have your type on the right, just the same, its own source. But as part of this bounds checking, so to say, you end up comparing a left type to a right type, but the right type needs access to data from the left. So basically what happens is you find your, let's say your equal trait, and you see that, oh, it requires that type parameter t of our class, let's say array, also implements equal over t. What it then does, it says, okay, well, we know we have an array of int, so our t is int. So then we compare int against that requirement of that bound. But that bound may refer to type parameters from the class that the trait is implemented for. In other words, it may refer sort of back to types from the array. So you end up where instead of traditionally you have left type, left data, right type, right data, you end up with like left type, left data, right type, left data. And my compiler didn't handle it. It would just overwrite stuff and basically do the completely wrong thing. Now I am fortunate to say that after 3 weeks of banging my head, and to be fair, I did have food poisoning for 1 week of that. I actually yesterday managed to reach a point where I can write tests. I don't have any compiler errors. But that took several iterations of the whole thing, and you know, very frustrating. I was pleasantly surprised that even my simple tests so far don't actually fail; they pass, which either means my type checker is broken or the tests are correct. Still have to figure that out. And as part of that, I also made some attempt at actually making tests a little less boilerplatey to write, because before just the setup code for a simple Typecheker is like 50 lines. Because it's saying, oh, we need a class, we need a type variable, we need to add a requirement, we need a blah, 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 blah.
Yep.
And then in parallel to that, as sort of an exercise, I've been writing a program in my language to control the centralized ventilation system in our house. I think the official English term is like hvac or something.
Yeah.
I think in the US that's also used for like sort of vacuum cleaning, I think.
Oh.
Or I might be confusing. Either way, this is like,
Yeah.
there's a big box
Yeah.
up in the attic and it sucks all the air off the rooms, pumps it outside and pumps new air in. That thing, ventilation. And the system there, the way it sort of officially works is you have the actual ventilation box by
So
default.
I think it's heating, ventilation, air conditioning.
Yes, some basically,
Yeah.
except the air conditioning part, because here in the Netherlands they haven't really learned air conditioning yet. So I'm still awaiting how summer is going to be. But so the basic thing is a dump box. It sucks out air, pumps it in, and then the company making this, they have this extra device that you can hook up to it to control rooms based on CO2 levels, humidity, the usual stuff. But then the big brains at that company decided, hey, you know what? What's a great idea? Using CO2 sensors in every room. Yeah, so we're not going to do that because that's too good of an idea. What we'll do is we'll put a central CO2 sensor up in this sort of airtight box, and all the rooms are connected to that. They exhaust their air into that box, and then it pulls it outside. And in that pipe that goes outside, there's a CO2 sensor. And then through a clever algorithm, or AI as it's called these days, they will sample rooms and try to figure out what the individual CO2 levels are, taking into account that while it's doing that, other rooms are still ventilated, etc. Sounds great on paper, sucks in practice. Because what happens, one, it makes a lot of noise, because it generally seems to favor waiting until the levels are too high, and then like, oh shit, we need to ventilate, really quickly. It has a tendency to ventilate the wrong rooms. So like we have people coming over, all sitting in the living room, the system's like, yeah, I'm going to ventilate the attic 2 floors up because I think the CO2 levels there are too high. And I found patterns where like if I'm in certain rooms for like 5-10 minutes and I monitor the thing, I can see like completely unrelated rooms, the levels also go up. Now, fortunately, this company, it's a Dutch company only, but people managed to hack it. Or specifically, somebody made a little Wi-Fi module that you can hook up to, and then you can control it, monitor it, etc. Because the thing by itself is a black box. And this being a company only active in the Netherlands, it's quite difficult to find details on how it works. And so for the last month, I've been writing a program to sort of take over this system in my own language, which, at starting I was like, how difficult can it be? But it's actually surprisingly difficult to get a ventilation system to both be quiet and sort of accurate in when it ventilates. Especially when you only have a central CO2 sensor, and good wireless CO2 sensors will easily cost you 200 plus euros. Because anything under 100 euros is either not measuring CO2, but some sort of related particle, or it's just complete bullshit. Like it will be accurate when the levels are very high, but below, let's say 1,000 parts per million, it's just going to be completely off.
Okay, so why do you have CO2 sensor requirements to ventilate as opposed to heating or cooling?
Well, so that's just for purely the air quality, right? So, levels go too high, you have to ventilate, because otherwise you don't suffocate, but you kind of get like drowsy.
You feel, right? Wow, okay. So like the house is so well insulated that you're just not getting airflow.
Oh yeah, this is like a modern built house, so it's pretty much almost airtight.
Like most of the European houses. It's not comparable to anything in the US.
No. So I've been led to understand that US houses are usually basically made out of cardboard, or like not that bad. Like fairly soft walls in that sense. Whereas here in the Netherlands, they're like, here's concrete, have at it,
Yeah.
brick.
No, it's all wood walls around here.
It varies
Right.
dramatically from part of the country to part of the country. But in the South, for example, they quite often use bricks because it costs less than wood, even though they grow the wood there, the big pine farms.
You grow the bricks there too.
They grow the bricks there and bricks, but get this, behind the bricks, there's no insulation.
Right.
Yeah.
It's
Yeah,
just like,
so that's
really?
here. I can only speak from Netherlands, but as far as I understand, this is basically most of Western Europe. Is since about 20 years ago, they really started emphasizing insulation, better ventilation, etc. So my previous apartment was an apartment block from the 1950s. This is basically before ventilation was a thing, and I was honestly surprised the place wasn't radioactive, because back then, like, everything had like uranium and whatever in it. The place did have asbestos, but don't tell the new buyers.
Right.
But so this house, this new one is, it was built a couple of years ago, so it's pretty much airtight, and very well insulated, great, etc. But that means ventilation is crucial. But so anyway, so this system, I built it using motion sensors. The idea being, if somebody's in a room, it doesn't really matter what the CO2 levels are. You should probably just start ventilating, because then you can also do it at a lower speed because you're earlier, etc. So yeah, I bought 7, 8, 9 motion sensors, like $50 a piece. I needed a Wi-Fi dongle. Then I later needed a computer to control the whole thing. And I figured, Raspberry Pi, I can't do a whole lot with it, so I'll just build a small computer. It all up and running. But that was a fairly good exercise, I think, for a programming language.
Yeah.
Because there's a bit of math involved. I had to do HTTP calls, and my language doesn't have an HTTP library, so I had to write one. A crappy one at that, but hey, it works. I want to have concurrency involved there. Right now, essentially, it works. There's sort of a single event loop where every 5 seconds it checks a bunch of inputs and sort of builds a list of changes and then applies them. But internally, different sources already have like different intervals at which they refresh their data. The ventilation data, I have it set to refresh every 15 seconds. So pulling it every 5 seconds is kind of a waste. But there was a sort of revelation that my language's concurrency system doesn't work for this. Specifically, the way I had it implemented, emphasis on had, I'll get to that in a second, is that you would spawn a lightweight task, you would send it a message asynchronously, you'd get back a future, and you could then resolve it into a value. And that value will be the return value of this function that you called through the message. And that's kind of great for sort of fork join style things, where you spawn a bunch of things and at the end you sort of collect all the results. It's terrible if you want to have stuff just run in the background and periodically send you stuff, because you can't do that. Because specifically the problem is for that, I have to take a step back here. So the message they work, it's kind of like a generator.
Yeah,
like you start a process, doesn't do anything by default. You send it a message, it runs that message, it waits for more. Right, and messages are run in FIFO order. So you end this thing where if I want I want to start a process, have it monitor some data, and just give me that data whenever it comes in. Ideally, you would start that process and say, hey, my process is this. And then it would send it a message every time it gets its data. And they would sort of talk back and forth. But you get that problem if the first process is running in an infinite loop, your main event loop. That second process can send it as many messages as you want. It's never going to pick them up. So instead, what you would have to do is you'd spawn the process, and every X seconds tell it, get the data. But then you might as well just get it in your main loop, because it's kind of the same thing, right? At this point, I had already sort of realized this, but this was a sort of reinforcement of it. And so The change I made there is that I haven't implemented, but my compiler doesn't work yet, can't test it. I'm using channels. So process, they still have messages. They still process them in FIFO order, but futures are out of the window. These asynchronous functions, they can't throw or return. And instead, they are expected to be given a channel to write their results to, or not, if you don't care. And then they sort of communicate through channels, but still by passing up ownership and all that. So there's no copying involved. And then what you would do is you'd create your channel, you'd spawn your process, you'd say, hey, every 10 seconds, write your data into this channel, and you will then check it, at your leisure. Yeah, I think the moral of the story that this started as like a small hobby project. Like, how difficult can it be? It's just ventilation. And yeah, I was slightly humbled. Let's call it that. I'm still fixing bugs. Or like bugs, like things like, the bathroom humidity goes up, so your system kicks in, and you say, I'm going to be clever. I'm going to say once you're below the acceptable levels again, don't immediately stop ventilating because it might go back up. Let's keep doing that for like 30 minutes, or in my case, 15 minutes. Well, what happens is apparently if you take a shower, the humidity levels go up, ventilation kicks in, humidity levels briefly drop quite a bit. They briefly drop below the threshold long enough to meet that time criteria, specifically around 16, 17 minutes. Ventilation is like, we should stop. And then it builds up rapidly again, and then it has to catch up. So you get this sort of like peak, bump, and then gradual increase, and then it takes quite a while to like reduce again. So you end up with all those kind of things where it's like, yeah, that wasn't as easy as I expected. But it's a great exercise.
Yeah,
I can highly recommend anybody who's writing a language, fix your ventilation with it.
It's kind of the same thing.
If you try it, until you try it.
Yeah, it's kind of the same thing. A couple of weeks ago, I built for the tech room downstairs a ventilation to get cold air in, or colder air, hopefully. It's kind of the same thing, right? You don't want blowing air if it's warmer outside than it's inside. But you also don't want to stop just immediately. You want to slow it down and keep it on a constant levels, kind of. So I hear you. The other thing you said you're looking into implementing channels. Is that like a queue or just a mailbox for a single message? I mean, in Go, you can basically say that is the size of the channel, and that is how many messages can store.
Yeah, so I have it implemented as it's a bounded queue, bounded FIFO queue specifically. My current implementation is like the worst performance-wise. It's basically a DQ with mutex. It's not atomic at all, and that's mostly because I have my own scheduler, and because my tasks are decoupled from OS threads. You can't use the usual mechanisms to like park threads and all that stuff. So the way there sort of works is it acquires the lock, puts a message in, then says, hey, did any process sort of register itself as waiting on a message with this channel? If so, pop it out of that list, unlock, and then we reschedule that process. Similarly, if you send, you lock, if you receive, you unlock the thing, say, hey, do we have messages? Yes, take it, lock it back up, off we go, right? And if not, we put ourselves sort of in the waiting list, if you will, and we just suspend. And so it's because of that, it's the implementation is probably a lot slower than that of many other languages. Although I have to say, I believe Go's channel implementation also uses mutexes. And looking at its definition, I was quite surprised by just how many different fields a channel has. So yeah, it's basically a bounded FIFO queue. I don't have the case yet where with Go you can give it a capacity of 0. And then what happens if you send and nobody is receiving the send blocks? That I haven't implemented. I'm also not entirely sure if that's useful, to be truly honest.
I haven't used
Yeah.
it.
Coroutines, fine. Push one thing, and then the other guy picks it up. He takes it. So you have one thing, and then you just the producer writes into a giant array. The consumer, there's only one giant array, so you block on the producer until the consumer's ready to grab, and he grabs the array and does his thing, and then he's done, and he hands it back to the producer by saying there's the queues of depth 0, and so everyone just hands it back and forth as a one-off producer. I don't claim it's a useful in general paradigm, but there is a use case for it.
No, I imagine so. I just at the time couldn't find it. I was like, oh, I guess you can just use a queue size of 1, close enough. But it's more like, okay, at this point, I can't quite figure out what you would use it for. I'm also not sure how you would implement that.
So
at least more efficiently than just.
I think the question is more, how do you unlock it eventually?
So right now, yeah, it's just the plain old mutex approach that you would expect from most.
No, I mean when you're waiting on a queue of capacities or on a channel of capacity 0, how would you unlock the writer that is waiting? Because you can't take anything off of it, right?
Well, so I'm thinking out loud here is the writer would unlock. It would see through some flag like, hey, we are a 0 capacity channel. It would check, are there any readers? No, we put ourselves in the waiting list and suspend. Then the reader, I would imagine, would unlock it. It would see, hey, there's a writer. It would then have to reschedule it, suspend itself. Then the writer would wake up again. It would say, oh, hey, wait, this is the first time after we, the first time we woke up. So that means we have to write a value. And basically repeats the process, sticks the value in, but then it doesn't suspend and goes on. And then the reader wakes up again, pulls the value. So it's kind of like
that sounds like a very go thing. So it's
basically the writer has to quote unquote write twice, if you will, but the first time it doesn't actually write anything.
Yeah, but you don't actually have to. It's symmetric, so you can do it in either direction. It's basically a handshake. The reader and the writer agree to meet, both alive and active at the same time, essentially.
Yeah, but
directly handed off from reader to writer.
But to be honest, if I have a channel of capacity 0, I should never be able to write anything. Even if there's a reader waiting for me, I can't put it into the channel, so it can't come out the other side. So that's what I mean. It's a go thing to do, so it's probably possible.
There's a usefulness for it for certain kinds of handshakes, where basically the message doesn't ever wait in the queue. The message is either here in the reader or here in the writer. It's never in the queue. It's directly one element is handed from reader to writer.
I would probably lean towards this being its own distinct type, to be honest. Like, as in, a channel has a capacity, can't be 0. If you have this sort of handover thing, I would almost say that's almost like a future or a promise if you will allow multiple reads and writes, but it's basically you have this box, the value can be in it or not, but
suppose you have a special thing of only one you can have. I was using big array, but you can imagine it's the GPU on the processor, and I want to hand the GPU off from me to you, and so we have to agree to be at a spot, and then we can directly hand the GPU off, but I can't make another GPU and repeat for any kind of resource I can only have one of, and I want to directly hand it from left to right.
Right. Yeah, and that's also where I'm not sure how useful it would be, because at least in my language, putting data in a channel doesn't copy it. I
Right.
think in Go it doesn't either, which is
Right.
how you can have race conditions still with channels, but you sort of move it into there, and so
You have a pointer to it that you've put in the
yeah,
channel.
you stick
Yeah.
a pointer in it, but
Yeah.
so that's why I'm like, in theory, I think you can get the same results by just having a channel with a size of 1.
Right. You have a notion of a thing that is either in this thread or that thread or waiting in the
Right.
channel if it's unused by anybody at the moment. Which,
Yeah, and so in my case, that idea still stays. Like you can still send messages to processes and give them arguments, and they are still moved from one process to another. It's more like for communicating results. That's where you can use channels, for example, or cases where you have like another example I ran into is my unit test runner uses processes for tests, so you can run a certain number of them in parallel. And ideally, what you want to do is you want to start, say, 10 tests, and every time one finishes, you start a new one. So you basically always have 10 running until you've reached all of your tests, and then it sort of tapers off. Rather than we run 10, we wait for all of them to finish, we run 10 new ones, etc. But basically what this requires is that you can spawn a bunch of tasks, and then you can efficiently poll them for completion. And every time you complete one, you just add a new one to the queue, or the work list, whatever you call it.
can you just
in
throw them
my-
all on the work list and the 10 threads pull from the same work list?
No, I mean conceptually, as in like you start with, let's say, 10 threads running, one finishes, you spawn another one. So that's of your work list. And then you have to like poll them, like, hey, which one is ready? Oh, these two. Okay, present their results, start 2 new ones. And the way I had that implement is kind of like that. You basically have a list of all your tests to run, a list of how many tests are currently running. You fill that list with 10 processes that run those tests. And then I had a method that would basically take an array of these futures, and it would return an array of those that are done, aka the poll3c function. And that way you could sort of produce test output as tests came in, start new ones right away, etc. But that poll implementation was pretty, because I think in the worst case you need 3 iterations over your input list of things to poll. Because there's one where you need to do an initial check, which ones are ready. As part of that, you also need to, I have to say this correctly. There's one check where you do, you test if they're ready, and if not, you push them in a, correction. You go over the futures, you lock them one by one, you say, does it have a value? Yes, okay, just return it. We're done. If not, you take that lock, you set it aside. And then your second iteration, you have to go over all those locks, and you have to say, we are waiting for a value on these futures. So you basically push yourself in their waiting list. And then you have to unlock them as part of that. And then towards the end, if it resumes, there's, if I remember correctly, another iteration to sort of collect those where we now had a value. Either way,
Sounds more complicated.
If you have a large list of futures, it's not great. I'm not gonna lie.
I mean, I don't know.
So that was in my crosshairs, so to speak, to to get rid of.
Because we did this kind of work a lot, both in H2O and in Azul, and
there's a whole reason why you have KQ, ePoll, all those things, because this mechanism, loop over a bunch of things to check if they're ready, sucks for performance.
Yeah, don't look at the promise implementation in Node.js. It is a horrible nightmare, because they don't just have the event loop, but they also have like 4 or 5 different priorities in which order tasks are being handled, just to make sure that all the promises are being handled correctly. It's a freaking nightmare.
Interesting.
Yeah, so with channels, I do have now a function where you can give it multiple channels and it will wait until one of them is ready. But that's essentially just a single pass. You go over it, you check, hey, is any ready? Okay, we bail out early. And And as part of that, you schedule it might be 2 passes actually. I have to double check. But it's mostly for cases where you have a piece of code and it has 3 channels, and it just wants to read from one of them. It doesn't care which one. So then you wait until one of them is ready, and then you act upon it. Admittedly, that's also on my list of things to potentially go, because it is a case that I've seen where you basically want to select from multiple channels. But it's also a case where I'm not entirely sure if this is the best way of going about it. Because in theory, you can introduce a sort of auxiliary channel where you have these 3 channels. You check if they have data. If not, you wait on this auxiliary channel, and then whoever writes to those 3 channels also has to make sure they write to the auxiliary one. It's not great, but in theory there are ways around it. But so this has been
push instead of pull or something.
Let me actually. Where's my? Let me check what I actually
Welcome
did.
To wonderful role of concurrency language design, or low-level concurrency language design. I mean, Cameron's saying services, basically channels between competitive, Erlang, not competitive, cooperative processes.
Yeah.
And,
so I checked in my case, my channel wait has 2 iterations over its input channels. One to sort of check and lock them, and then towards the end, one to sort of clean up once we've been rescheduled. That's basically it. So it's not terrible, but I think the difference here is also channels. I would expect you usually wait for a very small number, like a handful of them. You're not going to have like 5,000 channels that you're waiting for.
That was the I mean, yeah. People did the channel thing, and then immediately there was complaints about the 5,000 channel waits, and then they went
but so it's like when you have like, let's say futures, promises, whatever, like you have a computation producing 1 result, and you start, let's say, 1,000 computations. Yeah, that means you have to wait for 1,000 things. Whereas with a channel, you give those 5,000 things the same channel.
I have the thing that I did for H2O, which would do billions of that way, billions of futures, and efficiently and well, but maybe it's more of a special case here. But that was, you forked and you joined, and the master join that was collecting everybody who had to be all done to have those results ready had a list of folks that he was waiting on, that he would walk every time a new join operand got completed or wanted to throw on the list for. And he found that most of his tasks that you were waiting on would have already been completed, but that was not an alloc. That was an atomic bit set. So when you completed, you threw a bit atomically, and when you joined, you tested the bit. And then once he knew that that was, that one was done, he threw it off the list and lower his count, and every thread did that each as they came by with a new result. So when you completed your job, you went to I'm joining you, but I'm joining with a billion other guys. And I look at a queue of things that are all pending joins, and I discover that, most of them were done, and I cleaned out the done ones. And that meant that the list never got big, despite the fact that I was syncing millions a second. The list was 10 to 20 at most, usually 3 to 4. People got completed and somebody got in and then cleaned them out. And then the second thing was that because it was a fork and a join, that the split, when you were done, you set the bit, and if it was not set, then the other guy wasn't done. But if the bit was already set, the other guy was done, you're now the joiner, and you flip from doing the task that I wanted to do to now doing the join work that followed the task. So the usual story on the fork and the join was there was basically a map and a reduce, and the reduce followed. You mapped, and then you did a reduction with your pair map from the other side of the join, or the other side of the fork. And I could sync millions a second, billions in a big job doing that kind of a stupid hack. And I guess I could drag the code up and show people what was going on. It was actually not very much code, but it would handle a huge flow rate. And then after your billion things were done, some guy at the top of the queue would say, I'm the last man done with the billion things. And then I had a special hack that said, go back to the master Java thread that launched the whole thing with the end result. And he would wake up with the billion things done. But the actual, I did a join moment by moment, or I'm completing a task moment by moment was cas a bit, or check the bit was already set, walk a short list to clean up anyone else who was already completed and hadn't walked the list and cleaned themselves out. And then, and then if I wasn't done, I was the half that wasn't done, I threw myself on the list and then I got out of there. Went back to the work queue and grabbed something off the work queue. That was the standard worker process. I should see if I have that code lying around.
Do you have to worry about queue job size, like basically wasting too much time dealing with the queue process because your jobs were too small?
That was the fork join delight or madness, depending on your point of view. The concept on fork join was you had a large pile of work you're going to divide and conquer. So you split it in half and you threw it on the queue, both halves on the queue. Now the queue was length 2, each of which had 500 million things. And you pulled something off and it was 500 million is too big. So you split it again and you split and split. And the queue got an exponential power 2 drop off in size of chunks on the queue. So logarithmic size of chunks on the queue. When you got to whatever your default minimum size, and you had to specify your own minimum size, I think that this amount of work is sufficiently large enough I should stop and do it single threaded, or small enough I should do it single threaded. So the implementer, you chose how small was. But
would you include information about the total job in each of the jobs so that you could sort of say sort of where you are or anything, or they stayed?
No, they had the go backwards to the fork. They had a pointer to their forked parent. As an H2O implementation, I also carried around like the code I was going to execute for this job as a pointer to a Java object that was a Lambda expression. That was it had a single abstract method you're going to call on it. And you could do class games, and that would turn into like, if you wanted that information at a local or level, I didn't use it in the fork join stuff. If you wanted that information local level, then I usually put something in the key value store in the local task that asked the key value store for a copy of the master information. And every node then ended up with a shared copy of the master information that they were reading basically constants out of usually. For this particular job, I had constant things that needed whatevers. No, the queue was these powers of 2, and you stole from the small end, and you kept a little private queue yourself. There's all these mini-batching things going on to make it efficient, right? And somebody else who was bored and looking for work grabbed from the big end. So they would get the 500 million things, and that was too big, and they'd throw 500 million back, and then they'd look at 250 million and split it and throw 250 million back, and so on and so forth. So mostly when you stole from the queue, you stole a lot of work, and then you have to go back to the queue very often. And that's how the queue kept from being a bottleneck. But yeah, you could get, billion's a reasonable number. You'd get lots and lots of, the queue would build up, but it wouldn't get huge because of this exponential growth thing. And these tasks that you were doing, when you're down at the bottom level and you were done with one, the first man in would cas a bit saying I'm done, and then realize the other half's not available. You throw that on a to-do list somewhere for the other half, a join list. And then you go back to the queue with his own internal queue first, and then you go to the external queue to grab bits. And if you were the second man in, you immediately ran the reduction, and the reductions were guaranteed hard parallel. So it was parallel but deterministic, who joined what with what. You forked, then those two were the only two that joined. But there were different threads that were doing the join, but that was the join order, which is the reduction order. So you did the reduction, and then you joined again because, here's a pairwise thing. You broke it pairwise going out, you reformed it pairwise going back. And if you weren't, symmetrics. If you were the first of the outer layer of joins you just did, you threw it on the waiting for the other half partner done, and otherwise you did join work until you hit there. The thing that was,
it sounds a bit similar to the Clojure has this idea of reducers. I don't know if you've seen that. Except
no,
it doesn't do the exponential thing. It you have to have a collection that you can index into, and then it takes chunks of a fixed size.
yeah, I always had to be indexed into and took chunks of fixed size, but I distributed them across a cluster as well as parallel within the node.
Right.
But it was all, yeah, you had to be indexed. That was the 2D table.
Yeah, and I guess the exponential breakdown is good for the cluster distribution because you start by routing and then you start splitting. I'm thinking like,
yeah,
you get like chunks are so big you just split them and don't do anything. Then you must get chunks that are sort of large, and you say, I'm going to put this whole chunk on this computer, and then that computer can then subdivide further into actual threads.
So in the distributed cluster, the cost is to move data. So the data is kept on a node. So you actually distributed the first several splits were to distribute the job across the cluster according to the data that was available on that node in the cluster. So the first several splits were deterministic by how you did data layout.
Okay,
And
so you're not even moving those chunks of data; they're staying
yeah,
in.
they're there, so you just left them. So when the splitter came, he said, I'm going to split you by node. I don't know how much data is on which node. I don't care. I'm going to split by the node. So I did
Is this similar at all to like a different approach, but the same kind of idea to like the BSP graph algos where you have
parallel?
Yeah,
Yes.
you have sort of data sitting on machines, and
yeah,
messages are going between the machines about what the status of things are.
This was a log tree breakout to get every node to take off on their chunk of the data. And then within a node, they would do a log tree breakout as well, because you had to also do the reduction work, but you could do that only in a log tree. If you did it in a log tree fashion going backwards, then it was mostly parallel as well. So the long pull would be the forks going out were actually usually really quick. If you had any kind of decent data center, you'd have 16 nodes all running within microseconds. It would be 4 hops at a couple microseconds a pop per hop in your data center, and they were all running within a node. Again, microseconds for the OS to kick up all the threads. Then they would actually do the work, and then the long tail on the reduction is, it's the log depth of your data size divided by your whatever your mini chunking boundary is to do reductions, which had to be pairwise and therefore log depth in a node and then across the cluster. And that often meant you moved data for results across the cluster. And so that actually had some time if you're moving big results around.
Yeah,
and we mostly did BSP within an algorithm, bulk synchronous parallel within an algorithm. So you did a big pass over the array and a big pass over the array and a big pass. And then, depending on the size of your work, your ratio of the length of a pass versus the depth of the cluster and the like, you might find it efficient to run a second job while people were idling during the reduction rolls up that were not eating a whole node, but were in the network mostly. So jobs that were doing model fitting across large hyperparameter search spaces would launch several jobs until the cluster got pretty busy. But the fork join approach things, the implementation was detaily and boilerplatey and no language support, and the using of it was extremely easy. I wrote a Java program. I wrote make an instance of Mr. Task. He had a map call, which had a set of argument columns, which were arrays called chunks, but they were arrays. And I wrote a for I equals 1 array.length. Do math on array elements. And then I had a reduction that said, give me an instance of this Mr. Task and that Mr. Task. and do a fold up. And we had a lot of utilities to help with the fold up. So, you know, they had two arrays and you want to do pairwise sums of parts or pairwise whatever things. It was all utilities for that. And that level of work was easily understood by mathematicians and data scientists. So it worked out well. Implementing was, you know, casing and bit fiddling and stealing from work lists and very heavy concurrent algorithm. And that was half Dudley and half me, depending on which piece we were working on. So yes, in answer to Alan's unspoken question, I'm always looking for a better way to write that kind of concurrent algorithm. I didn't get much help out of it in C, and I didn't get much help for it out of Java. But they were very useful algorithms to have lying around. All right. I've done my H2O rant for the day.
I actually dropped the link to the Node.js documentation a little bit earlier.
Yeah.
And it is a 6-step a stage operation. And my personal favorite is the following diagram shows a simplified overview. And they already show 6 stages. I'm like, yeah, sure.
There might say Joe Armstrong from Erlang fame had a presentation a couple of years ago. I think it was titled "The Mess We're In." Probably one of my more favorite presentations. And he goes on about some complicated piece of code that's nearly 1,000 lines long, very difficult to understand. And there was only one comment in it, and it said, "And now for the tricky bit." It was like following some discussion about that the best form of documentation was a book or something like that. Yeah, it reminded me of this.
I don't have an H2O with source lying about. I ought to. Exactly, this is the demo for it. Fine. And now for the tricky bits. Yes. I'm hoping I have more comments than that, but you know, fine. Maybe, maybe not.
You know, the talk about channels has kind of gotten me wondering, and I'm just thinking out loud here. How similar or dissimilar is the approach used in Golang, for example, where they have channels? How does that compare with what was used for Erlang, where they're doing message passing, versus how were they doing it in Smalltalk, which was all message passing, you know? No concept like futures, like what we saw in Java, but is it just the same idea over and over again?
So
I thought message passing in Smalltalk was different from what we're talking about with actors and Erlang and Go.
It was mostly fake, but yeah. It was mostly method calls, not actual messages.
Right.
Yeah, I don't think Smalltalk in itself ever really. So if I remember correctly, the original idea that Alan Kay had of messages was much more closer to Erlang. Where like literally you send a message and it can be a method, it can also be a thing on a remote machine. Smalltalk itself went more with a message calls a function setup at some point, but not direct, like you could remap it and catch it, whatever. I think there's an implementation called ambient talk, if I remember correctly, which did this with actors, where you can have like actors on different networks and yada yada, using the Smalltalk language as a base. I think that the things, if you compare Go and Erlang in terms of concurrency, they are very similar in the sense that using an Erlang process, you can implement a channel. And I believe the other way around is a little more difficult. although you probably could do it also. I think the main difference is with Erlang, you can have, or typically with these sort of actor-based things, you can receive a message at any given point. Like literally at any point in the code, you say, oh, you expect a message at this point. And that works for Erlang because it's dynamically typed. And it is, as far as I understand, pretty decent pattern matching. That's how you usually receive a message. You don't say, I want a message. You say, I want a message of this structure. Whereas typically in a sort of channel approaches, you need a reference of some sort to your actual channel to receive data from. But I think beyond that, it kind of comes down to like how in a lot of like modern languages, it's not really clear if it's like functional or object oriented, because it's kind of both. There's like so many overlaps. And with channels and actors, I think the usual difference is that actors, at least on paper, the idea is that they can be on different machines, whereas channels is usually something just in process. But even there, you could argue, well, you could do that with a channel. It's called, RabbitMQ, basically. So I think it's a mixture of sort of opinion.
I think maybe you hit on one of the fundamental differences. I'm just thinking through this, right? That in an Erlang process, and to be fair, I've never used Erlang, I've only read about it, right? The process has a mailbox that's associated with it. Whereas when you have channels, you've really detached it, and that's now a first-class citizen. The channels can be passed around to different parts of the code. It's not that you have a bit of code with one mailbox anymore.
You have many producers and consumers on the same channel.
Yeah.
Massive.
Yeah. I mean, yeah, in Go, you can. I think it is a multi-producer, multi-consumer, if I remember correctly.
Well, you can pass
yeah,
about,
you can.
how are you going to stop that?
Sorry?
I mean, if you pass about a channel, how do you stop it from being a multi-producer, multi-consumer?
Right. I think in Go, it kind of had to be because you can't guarantee that there's only a single on either end. Like Rust channels, for whatever reason, they are multi-producer, single consumer, if I remember correctly. MPSC, a multi-producer, single consumer. But it can enforce that through its ownership system. I don't know why they went for single consumers, but that's what they did. Like in my case, I'm just going to make my channels multi-producer, multi-consumer. But yeah, it's true. Like channels are usually actual values. You can compose over them. You can kind of do it with processes too.
There's a thing with multi-producer, single consumer. I'm calling up something from Martin Thompson's disruptor pattern. There's like an efficiency hack that works when you're reading and not writing or something. And I don't have it right in my head, but I mean, the way he normally works his channels is somebody, the reader never, how does this work? Damn it. This is like the one core only ever writes to one value, which is his pointer into the shared queue, and one core only ever writes his value into the shared queue. And there's a way to make that stack with parallel writers, but not parallel readers or something. I'm not positive here. But there's a high efficiency hack you can get in one direction. And I don't remember why it doesn't work in the other direction. And maybe I'm just all confused. These are all things that would be useful. Pull up disruptor pattern and stare at what he does, because he does get like ludicrous throughput out of that thing. So no one cares. All right, fine.
I think one thing I can add to there. One thing I had in my implementation was that the futures that I had, they were sort of implicit. As in, if you asynchronously call a function, you'd get a future back, and that function would write to it. But I had this idea like, oh, if I create a future twice, one for the reader and the writer, that's kind of wasteful if they're heap objects. So there was a bit of an optimization where instead the receiving message instead had access to sort of the internal data structure, but wouldn't actually create a heap object. But then you end up with these complexities where you have to sort of inject generated code that says, oh, if we failed to write into that future because the receiver discarded it, then I actually have to take the message back, drop it. I think my sort of revelation in all of that.
Bobby.
Sorry?
Sorry, go ahead. Bobby put something in the chat that should be in the doc, which maybe it is. Be in the doc.
Basically, my moral of that story is that I've come to prefer that being explicit, as in not the compiler inserting code like that. Rather make things a first-class value, so it sort of all goes through the usual mechanisms that are already in place. Like if it was a first-class value, you would handle this using destructors. So if we drop a future, the destructor checks, does it still have a message? Yes, okay, also discard the message. And then you would be able to reuse, like if your language has destructors, that would already be implemented basically. So you could reuse that rather than having your own sort of special source for this one specific type. For me, that ended up being another reason why I kind of moved towards channels, because they're a little nicer as first-class values, because they're a bit more useful. And it makes your compiler implementation easier. It's less code to generate.
It's the runtime. Okay, yeah, fine.
So are you, sorry, maybe I missed this, but are you backing your channels with queues?
Yes, they are bounded FIFO queues.
Oh, okay.
Block if you get full. Or reject.
Yeah, it's part because I think it makes the most sense, and part because it's a little more efficient to implement. You don't have to reallocate at runtime.
Well, the options are grow the queue until whatever, or block or reject. Like the general rule for producer-consumer relationships in general is one of the two is always outrunning the other. So either the producer only produces faster than the consumer will take, and you'll build up to-do work until you choke and die, and you must have back pressure. Or the consumer can keep up with producers at any level, and therefore the consumers will just take, the producer can fucking wait because the consumer will grab it before he'll actually wait. As soon as the producer's got something done, he says, I'm done, it's gone, and he just goes back to going again. So this is the usual load factoring. And only if you have brief spiky moments do you actually care for a queue. Usually one side or the other is always winning. And now, does it make sense to have bounded or whatever, given that one's always winning on the other, or you want to rebalance or something? I guess the other piece of that was headed for was the back pressure must be implemented. If the producer can win ever, then the back pressure must be implemented. You'll get it whether you like it or not. So if you have some control over it when you're getting it, you'll get a better answer out. Does that make sense? Producers producing without bound, you'll run out of memory. So instead you've got a fixed queue. Okay, your producer blocked. Now your producer's not consuming from somebody else. So somebody else is producing for him, fills up in blocks. So there is a back pressure whether you love it or hate it. And then now it makes sense to talk about the back pressure. I guess it's network flow theory.
Yeah, I think it comes kind of to preference. Like I've used both bounded and unbounded channels in the past, and I have to admit, whenever I used unbounded ones, it was because I was too lazy to think about what the capacity was that I actually needed. It's just like, just get it over with. I just want to put my stuff in a channel.
Seems like it would work as long as your program doesn't run for too long.
Exactly.
Yeah, basically. Yeah. Or as long as you're the only user of the program.
Yeah.
I think in general, like with any sort of data structure that, with any data structure that involves concurrency, I think having it of a fixed size capacity is probably the best start. It's not necessarily always the best solution, but the best starting point. Because I think it's better to run into a case where it says, oh, we're full, so we either block, throw an arrow, whatever it is, rather than Sorry, we're now using 8 gigs of memory because there's no limit on this thing.
And then you throw out a memory.
Right, and then
Just
it's
crash
like
instead.
your OS starts killing some random unrelated process because you're on Linux and
Yes.
the out of memory killer is shit.
Well, the other
So it's
job
like-
is you get a full GC cycle that takes 10 minutes, and everything's unresponsive.
Yeah, it's so basically, yeah, throw an early error or block rather than just more memory.
Yeah.
Yeah.
That's actually, I think that's the right answer. Never say unbounded queue, but you can tell somebody they're allowed to have a large queue, but not an unbounded one. And
Right, you can just say, "Oh, I don't know how much you need. I guess I need a queue of 10,000."
I'm about to say, make it 1 million. It's like ludicrously big. You probably won't run out of memory and die, but if you hit 1 million, you'll realize you have a problem that you have to deal with a different way. Something so big that it would be like, obviously, this is stupid and not working, but it's not necessarily a crash. And of course, I guess somebody would just abuse it and live with the
I
million.
mean, I checked 1 million. At least if you stop pointers, 1 million it's only 8 megabytes of pointers.
Just the pointers alone. Yeah, never mind.
Ignoring the objects behind it, of course.
Yes, yes. Well, but only 8 megs. Now you assume you got 100 bytes per result or 256 bytes per result, and you're up to a couple gigs.
Yeah, I mean, if you have like,
laptop
I don't know,
might not crash.
32 bytes per object, still you have plenty of memory.
Right, so it's probably not crashing. But it's clear that you screwed something up. Fine. Yes, in the land of H2O, I could not have unbounded queues because I would totally spew them out to the limit and you would die. That was many early failures. We fixed that soon. That one killed me quite early. All right. What else? It's 11:30, hour and a half. We can be done. You got a nod? Yes, we can be done. Okay. I have company here too, so I can watch.
Yeah, I mean, we don't have to try to
Push
beat the 2 hour mark every time.
Right. I'm with you in that. It's not required to have a minimum time. It's quality, not quantity. Okay. All right. I'm going to call victory. Any last minute comments? 3, 2, 1.
Was nice seeing you. Goodbye.
Yeah. See you next week. Bye.